Hey kids. All right, so last time I gave you this little puzzle here. Is this an okay proof that 2 is equal to 1? Before I answer it, I just want to ask you a rhetorical question here because even if you yelled out the answer, I couldn't hear it. What does 3x over x simplify to? And many of you have been taught that you can cross out the x's and it's equal to 3. And that's pretty fair because if x was equal to, let's say, 1, we can say that 3 times 1 divided by 1 is 3. And if x is equal to 2, then we could say that 3 times 2 divided by 2, well, that's still 3, and so on. It doesn't matter what value of x I put in there, multiplying by x and dividing by x cancel each other out, and the effects are basically that nothing happens. So we should be able to cross the x's out, right? But if we're going to cross them out, we got to make sure this works for every single value of x. And here's the little twist. X is equal to 0. Is it true that 3 times 0 over 0, is that equal to 3? And the answer is no, it's not. Because when you divide by 0, it is undefined. We don't know how to divide by 0 in math. It doesn't make any sense. So it's not fair to say the x's always cancel. This would be true only if x is anything other than 0. So what we have is we've got a little bit of an issue here, and this is going to permeate this entire unit. We can usually do some canceling, but we got to be careful what the numbers are. You can't just cancel x's if they happen to be 0. So what does this have to do with this puzzle over here? You'll notice at some point we did some canceling. This guy here and this guy here canceled out. That's what happened. But what do we do when we're canceling? We're not just crossing things out, we're dividing both sides by that factor. And when you divide both sides by a minus b, what are you really dividing by? If we start with this idea that a and b are the same thing, then a minus b, well, that's equal to 0. And what did we do to both sides? We divided both sides by 0. And this is where the problem is. So if you answered probably step 4 is not the problem. Step 5 would be the problem. There's nothing wrong with writing a minus b on both sides, but when you cross them out, this is the issue. Okay, so what we did is we illegally did something here. And if you want to maybe make this make sense in terms of numbers, I could do something similar. I could say 2 times 0 is equal to 1 times 0, couldn't I? That's true because both sides are 0. Am I allowed to just cross the zeros out? Then I would say 2 is equal to 1. Nope. So that's the issue, okay? So don't worry, life is good. 2 is not equal to 1, and someone just cheated. And a lot of these kinds of things online wind up having this issue where you can't cancel zeros. Okay, so the idea of canceling zeros, the idea of having zeros on the bottom, because what we're doing when we're canceling is we're dividing. Dividing by 0 is a big issue. That's what today is about, and let's actually get looking at the lesson. So, section 6.1, equivalent rational expressions. I get the joke, it's hilarious. Okay, so we're going to start by defining what a rational expression is. It's very simple. A rational expression is a fraction or a ratio where the numerator and denominator are both polynomials, so things that have x's and basically nothing else, x to the power something. Polynomials have terms with non-negative integer coefficients. This is probably not the most important thing for you. It's just worth mentioning. I think we generally know what polynomials are because we've been looking at them since certainly grade 9. And of course, they may have constants or coefficients, but they might not. So just a quick little example, which of the following are rational expressions? So it has to have non-negative integers, so it can have an exponent that is 0, 1, 2, 3, 4. When we look at this, is this a polynomial? Yep, it is, because x has an exponent of 2, this x has an exponent of 1, and even though we can't really see it, this has x to the power of 0, because x to the power of 0 is 1. So even though you can't see it, they would be there. Now this is over 2x. So we've got a polynomial up top. 2x, it's not a very complicated polynomial, but it's a polynomial, therefore it is rational. Okay, so this is what we're talking about when we're talking about rational expressions. This one here, we can see the exponent itself is actually x, and that doesn't really fit the bill here. We have to have non-negative integer coefficients when you've got a variable up in the exponent. That is not a polynomial, and I mean the bottom is a polynomial, but therefore it's not a rational expression. If you're wondering what the actual name would be, I don't know what you'd call this, but I can tell you this is an exponential up top, so the whole thing altogether is not rational. Okay, and then this one here. So 14 root x minus 6 over 3, is this rational? This is equivalent to x to the power of 1/2, so that makes it not a polynomial. Remember, for a polynomial to be a polynomial, it must be an integer exponent. Is 3 a polynomial? Technically it is. You can express this 3x to the 0, so it does get polynomial status, but it's kind of a weird way of saying it. Anyway, this one's not rational as well. Okay, this is not the most important part, but I just want you to understand what you're looking at, polynomials over polynomials. That's what this unit's about. All right, so the big meat and potatoes of this whole thing, the non-permissible values. So what it is basically a denominator can never be 0, and any value of x that makes this happen is non-permissible. So if we look at this, what are the non-permissible values of x in this expression? No one cares what happens up top. The top can be 0, negative, positive. It can be your best friend. It can be anything you want. The bottom absolutely cannot be equal to 0. Never equal to 0. So if you want to get the non-permissible value, which, by the way, non-permissible value, that's way too much. So this I'm always going to call NPV for short. So what are the NPVs of this? What you do is somewhere off on the side or wherever, you're going to go x squared minus 2x. You're going to set it equal to 0 because that's how you're going to solve for the values of x that will make it equal to 0. Those are the bad values. So the non-permissible values here will factor x out, and we can see that x equals 0 and x equals 2. So what I would say is my non-permissible values are, now there's a little bit of a notational thing. You could say x is equal to 0 and x is equal to 2, but you tend to see them in textbooks with the line through as in x is not allowed to be equal to 0 or 2. There's two ways of looking at this. One, you could say this is what the non-permissible values are, but I'm a big fan of just cutting to the chase and saying x is not allowed to be 0 or 2. So I'm usually going to put a line through the x there. I think we're all just going to understand what that means. Okay, this next one here. So we're looking at the non-permissible values. So we say, what are the NPVs? You grammatically shouldn't put an apostrophe there, but whatever, we're just going to put it in. So the non-permissible values. So we've got x squared minus 4, and we've got x equals to 1. So what we're doing is we're going to look at just the bottom, because no one cares about the top. And we're going to set that equal to 0. What are the values of x that make this equal to 0? We can look at this one here. This is x is equal to -1. X squared minus 4, this can factor into a difference of squares, right? So this here is the same as x plus 2 and x minus 2, which means x equals -2 and x equals 2. So putting it all together, what are the values that would make the denominator equal to 0? -2, -1, and +2. Those would be the bad values, okay? So when you are dealing with something like this, you can evaluate this, but you definitely cannot have x equal to 0 or 2, and on the bottom one, you definitely can't have x equals 2, -2, or -1. You can even try it. If you put in x is equal to, I'm just going to put in 0 up top here, just as a quick example. Can you tell me what this is equal to? And of course the answer is undefined, right? So there's non-permissible values. Okay, canceling. So when we're talking about restrictions on x, and that's what we're doing with these non-permissible values, they always come from the original expression. Even if the term's canceled out, you got to keep the restrictions on x. So what we have here is we have an expression that can be simplified. So the way you simplify these expressions is see if anything can cancel out, and that usually happens after you factor. So what we're going to do is we're going to factor an x out of the top, and then we're going to factor the bottom. So I can see I can factor an x out from the bottom as well. When we're here, you don't necessarily want to start crossing things out, and you may or may not get your non-permissible values right away. You maybe see what they are, maybe it's very obvious, or maybe you need to factor a little bit more. X squared minus 25 is the difference of squares. So there's the x plus 5 and x minus 5 here. Okay, before you start crossing things out, you definitely want to get the NPVs. So NPVs first, then cancel. So NPVs, then cancel. Usually I would factor before I get the NPVs so they're easier to see. Do it in these three steps in this order. So factor, non-permissible values, and then cancel. Right? So when we look at this, the top, no one cares about the top. It's not important. The bottom, we can see that x cannot equal 0 or -5 or +5. So somewhere, I don't care where you write it exactly, but somewhere you have to write this out. So -5, 0, and 5. It's nice to put them in ascending order. And once you've done that, once you've written down your non-permissible values, you've said these are the values that I cannot compute this for, now you're allowed to cancel. Because as long as x is something other than 0, -5, or 5, x divided by x will always be equal to 1. If x was like 4, then 4 over 4 is 1. If it's 6, 6 over 6 is 1. Well, you get the point. X plus 5 and x plus 5 also cancel out. You must cancel entire brackets. You cannot selectively just grab the 5 and cancel it with the 5 down there. That does not work either. So you have to cancel entire brackets. Anyway, so this whole thing here simplifies down to 1 over x minus 5. So this complicated thing here is equal to this simple thing here, as long as x is not one of these three values. Okay, next one, 4 minus x, blah, blah, blah. Well, you guys can read. So what I would do first is I would rearrange things. I would go 4 minus x here, and on the bottom, you can factor this out to get x minus 4 and x plus 1. Okay, so 4 minus x and x minus 4, do those things cancel out? They almost do. Here's a little trick. If you want to change the order of a two-term, I guess this is a binomial, and there's a subtraction sign, you can factor a minus sign out of it, and they'll flip around. The full story is you would write like 4 minus x is negative x plus 4, and then you would factor the negative sign, which switches the signs on them. That's what I did, but just sort of in a shortcutty way. Okay, now before I start crossing things out, so I factored first, now I want my NPVs. I can see that my NPVs, x cannot be equal to 4, and x cannot be equal to -1. So somewhere off on the side, I'm going to write that x cannot be equal to -1 or 4, put a little box around that. And then I'm going to cross things out with my amazing blue pen crossing. So x minus 4 in brackets cancels with x minus 4 in brackets. You have to cross out the entire bracket. Then we're left with a minus sign on top, which can be interpreted as -1, and we've got x plus 1 on the bottom. Life is good. I would leave it like that. You can try and do some other weird stuff if you want to remove the negative sign up front, but that's good enough. Okay, here's a couple more examples. So write each equation in simplest form. So we're just doing canceling, which is not really complicated. The only thing we're really focusing on is making sure we get our non-permissible values. So for the first one here, I don't have to do any factoring to see my NPVs. I can see we've got x on the bottom and we've got y on the bottom. So this tells me that if x was 0, that would be bad, and it also tells me that y being 0 would be bad. So those are both my non-permissible values. The fact that they're squared, that doesn't make any difference. 0 or 0 squared, it's still 0. So what I'm going to do now is I'm going to do some canceling, and this is something that you're probably familiar with. X squared and x squared are gone. 2 and a 4 can be replaced with a 1 and a 2. Y cubed cancels, and then this entire y squared cancels. What's left when we're done with everything? we have a 1 and a single y up top. So we've got y, and then on the bottom we've got a 2. So this is y over 2. Okay, next one here. Looking at the bottom, we've got x plus 1. We can see that if x was equal to negative 1, we'd have a problem. So we're going to go x cannot equal negative 1. That's it. And of course, this example is chosen because we can see x squared minus 1 factors into x plus 1 and x minus 1. This one's x plus 1. And of course, we can simplify this entire bracket with this entire bracket and get x minus 1, and that's what it simplifies down into. Okay, and then for this one here, actually, you know what? We're just going to hold on one sec. Before we go to the next one, I actually just want to show a picture here. So I'm going to see if I can go over to Desmos. Get out of here. There we go. Okay. This equation, this is one that's interesting to show on a graph because this looks like a complicated equation with a complicated graph. And if you go to plot this, you go x squared minus 1, and then you divide the entire thing by x plus 1. You'd think you're getting a complicated graph, but you're actually getting a remarkably simple graph. You get a perfectly straight line. And what we did when we simplified is we said this complicated expression simplifies to x minus 1. Well, this is the line x minus 1, right? It has an intercept of negative 1, and it has a slope of 1, so it's just y equals x minus 1. That's what it is. Now, there's one thing. This complicated, we'll call this a line, and this simple line are the exact same, but we did say one thing. As long as x is not equal to negative 1. So one thing I want to show you here is if we zoom in on our graph, and you can't see it on Desmos, but if you find where x is negative 1, and you go and you click on this point right here, Desmos gets upset. It says negative 1, the y value is undefined. So there's actually a little tiny hole in the graph, and you can see it right there where my cursor is pointing at. Every other value is defined except for that one there. Now if I hide that and I do x minus 1, which is in blue, and I go to click on that point, it is defined. So as long as x is not equal to negative 1, these two graphs are identical. And that's the same thing as me saying that these two expressions are identical. So anyway, there you go. More detail on that in grade 12. For now, I just wanted to show you the graph to make the algebra hopefully a little bit more sensible, not just so abstract. Okay, the last one here, we're going to factor this out. I think this is pretty easy factoring. X plus 3, x plus 2. Yeah, so they add up to 5 and multiply to 6. NPV is here. X cannot equal to, and I can just see it's negative 2 and negative 3. And look at that. Does anything cancel? Some people will be tempted to like maybe cross out those 3's or something like that. That does not work. You cannot do it. You have to simplify the entire bracket. So x minus 3 and x plus 3 are not the same thing. So there's no simplifying. This is the final answer. That's as good as we get. But we do have to write the non-permissible values. Okay. One more, two more, I think. Last slide. Is this statement true? Is this complicated thing equal to this simple thing as long as we say x cannot be equal to 5? So when you look at this, you go, okay, well, that makes sense that this is the non-permissible value because if x was 5, we'd be divided by 0, and that'd be bad. But what is this guy here? This guy is actually x squared minus 1 over x, well, we better do some factoring actually. I'll factor the top and the bottom. So this one here, this actually factors into x plus 1, x minus 1. And what does the bottom factor into? Let's see, two numbers that multiply to 5 and add to negative 6. That must be negative 1 and negative 5. Okay, we can see that the x minus 1's cross out, but only after we give that non-permissible value. So was this statement true? We can see the simplification look good. X plus 1 and x minus 5 are what's left over. But what's missing here? we also have to say 1. So I guess the answer to this would be false. We need the non-permissible value x cannot be equal to 1 as well. Most questions of this nature will be testing you on whether you are getting all of the non-permissible values or not. Okay, and then finally this one here, state the domain of. Okay, so this should actually say like y equals 3 minus x over x squared plus 4. The reason I chose this, maybe I'll just shove the y over on this outside. The reason I chose this example is it was just a little bit of a different way to ask the exact same question. So state the domain of. The domain is all the allowed x values, or everything but the non-permissibles. So everything but the non-permissible values, or you might even say just the permissible values. So what is the domain of this? What values of x am I allowed to put in here? So x squared plus 4 equals 0. This is how I'm going to solve for the NPVs. So when I go and I do this, solving for the NPVs, I go x squared equals -4. And at this point, maybe we square root both sides. And here you might have a little bit of a heart attack in you, huh? So just remember, what is the value of x that when you square it, you get -4? Right here we can see that x squared is always greater than or equal to 0. Therefore, all x are allowed, or not allowed, I'll use a more mathematical word. I'll say all x are solutions. That's what we're doing. All x are solutions. Every value of x, every number out there under the sun, if you square it, provided it's a real number, if you square it, you get something that's positive. So it will never equal -4. So what are my non-permissible values? Therefore, there are no non-permissible values. Therefore, the domain is all real numbers. There is no value of x that messes this up. There is no value of x that when I graph this, I get a hole in my graph or some other weird problem. And if we want, we could just jump to Desmos and actually see it, because I think it's always satisfying to see. X squared plus 4 on the bottom. No one is requiring you to know what this graph looks like. That is something you'll look at a bit more in grade 12. Even this is a little bit tricky to totally get. But if we just look at the graph, we can see it's just kind of this speed bump sort of thing. And there is no value of x that screws it up. If you just go around and you click on it, you'll always get values of x, okay? And that's because there are no non-permissible values. This isn't a question I had planned, but just in case you're wondering, could we make something with non-permissible values? Absolutely. Let's change this from a plus to a minus. X squared minus 4. Now you can see the graph goes really weird. And the reason why it goes really weird, that's because when x is equal to 2, so I'm just going to make this a line, x is equal to 2 or x is equal to -2, those would be non-permissible values here. And you can see what happens to a graph when you approach a non-permissible value. It gets all messed up. Anyway, that's starting to get into what Pre-Calc 12 looks at. That's just a little part of it, but again, it's worth looking at. So this is just sort of the introduction to all that stuff. But basically, non-permissible values mess up graphs would be a good way to summarize all this. Okay, anyway, that's the lesson. Thanks for watching. See you next time.